Welcome to today's lecture, and today's lecture will be about vibration absorber. So what are we talking about? We are still talking about the model that you have seen in previous lectures, and you remember that this was a model where we had two coordinates, coordinate x and coordinate phi. X was describing the vertical bounce and the coordinate phi was describing the pitch motion. Now, when I want to show the vibration absorber, I want to go back to a more simple model, and that simple model will only describe vertical dynamics. So now we are looking at a new coordinate x car, which is comparable to the x that we had before, and we are no longer looking at the pitch coordinate. This makes the system a little bit more simpler. It's a 1 degree of freedom system. We remain the excitation from the road, and we describe the spring rate and the damping through the parameters C car and K car. And now we add a so-called vibration absorber, and that is an additional mass which is connected to the original mass m car by a spring, and the spring is called C absorber, and a damper which is called K absorber. Usually the mass that we add to the system is only a fraction of the mass of the car, so m ups is much smaller than m car. Now, what do we do with this system? In fact, we also want to set up the equations of motion, and you can already guess from the fact that we now again have a system that is described by two different coordinates that we have to set up two equations of motion. And in order to come up with the two equations of motion, we need to draw again the free body diagram. We have to look at the forces that are acting on the absorber mass, and we also have to look at the forces that are acting on the mass of the car. And here you already see that when we are looking at the absorber mass, we have a spring force and a damper force, and both are determined through the coordinates that describe the motion of the absorber mass and the motion of the car body itself. Of course, you also know that those forces that are acting onto the absorber mass can be refound as forces acting on the car mass, but of course the direction of the forces is just the other way around. Additionally, on the mass of the car, we have two more forces, and these forces are through the stiffness and the damping rate of the suspension system, and we also see the excitation S of t when we are talking about the spring force, and S dot of t, the first derivative of the excitation with regards to time when we are looking at the damping force. So based now on the free body diagram, we can start to derive the equations of motion. And first of all, we can formulate Newton for the absorber mass. And you see that we are just looking at the sum of all forces equal to mass times acceleration. And the forces that we see are just the two forces coming, first of all, from the spring that connects the absorber mass and from the damper that connects the absorber mass. So this is the damper force, and here we see the force from the spring, and obviously, as you can see from the free body diagram, these two forces are counteracting the coordinate of the absorber mass. That's why we have two negative signs in front of the forces. Now, when we formulate Newton for the car mass, then again the sum of all forces is equal to mass times acceleration. And what we can see, first of all, is that we have the damping force from the absorber damper, and we also have the spring force from the absorber spring. but obviously, since now these forces are counteracting the forces that we previously saw acting onto the absorber mass, both are now connected with a plus sign instead of a negative sign. These are not the only forces that are acting on the car mass, but we also have the forces coming from the excitation from the road. So it's the force that represents the spring force and a force that represents the damper force. And obviously these two forces are counteracting the positive direction of the coordinate x car. That's why we have a negative sign in front of both these forces. So that explains the forces. This explains the Newton for absorber mass and Newton for car mass. And then we can put together the forces such that we get the equation of motion. And then we see that the first equation of motion is a homogeneous equation with 0 on the right-hand side, but the second equation is non-homogeneous because on the right-hand side we have excitation terms, and there are two excitation terms, but we've seen that previously from other examples. One excitation term deals with the damper force and the other with the spring force from the excitation. Now we have to look at the solution that we get for the two coordinates. And in fact, the solutions that you see here are very similar to what we have seen for other excitated systems. But here we have the opportunity to look more closely into what happens. And we can see that the amplitude of the coordinate that describes the motion of the mass of the car is such that we can formulate that this should be equal to 0. And that's very interesting. And what we see is that there is a certain condition depending on the spring rate of the absorber and the mass of the absorber that we can reach that this equation is equal to 0, because obviously the second condition that we might be able to deduce, that the spring rate of the car suspension system is equal to 0, is a non-valid solution, because obviously we want to have a car with a non-zero suspension spring rate. This means that we can now solve for omega, and it means that given certain values for the spring rate of the absorber and the mass of the absorber, we can come up with angular frequency which correlates to the fact that there is no motion, no vertical motion of the mass of the car. So that is the so-called absorption point that we can define. And in this example, we see that we are talking about a very low velocity related to this angular frequency, which in this case would be slightly above 4 kilometers per hour. Now, what does the frequency response look like that we see for such a system? You see on the left-hand side the system parameters for the masses, damping rates, which are here set to 0, so it's a non-damped system. You see the spring rate of the car suspension system, the spring rate for the attached absorber mass. We also see the amplitude of the excitation, and we also see the length of the excitation. And now you can see that we can plot, first of all, the amplitude of the car body, which is the black line. And interestingly, you see that this is exactly the absorption point we were discussing previously. And since we are talking about a 2 degree of freedom system, both coordinates, the amplitude of the car body and the amplitude of the absorber, have resonance 2 times. Here's a resonance and here's a resonance. Now let's look at the simulation that shows us the behavior of the mass. You also see the initial conditions, no velocity, but certain values for the coordinates x car and x apps. And shaded, you see the 0 position. So we start from an extended position, and now we can start the animation. And slowly you can see also from the displacement versus time diagram, you see that almost exactly the two masses are moving with the same amplitude, and you can see from the diagram this is very low velocity, nothing much really happening, just very small displacement that you can see. Now, when we are getting closer to the first resonance, we can see that things change slightly, and in fact we can see that the amplitude of the absorber mass is getting much higher than the amplitude of the body, but still both the car body and the absorber mass exhibit higher displacement amplitudes than the excitation. Now we can go to exactly the absorption point, which is close to 4 kilometers per hour. And now we can really see also from the simulation that the mass of the car body remains stationary. It's just the absorber mass that is vibrating. So this is exactly the absorption point, meaning that we are now able to more or less completely reduce the vibration of the car body to 0. If we are going again towards a situation where we are supercritical, so here higher velocity, then we can see that still there is vibration for both the car body and the absorber. Now they are vibrating against each other, so it's not in phase but out of phase, and still we can also see that since we are supercritical, the bodies are moving with smaller amplitudes than the excitation. The frequency response diagram that I've shown previously was based on two resonances that were quite close together. We can also use other values for the system parameters. Of course, since we are still talking about the same car, we didn't change anything about the stiffness of the car spring rate and the mass of the car, but we changed now the stiffness, the spring rate of the spring that connects the absorber mass with the car body. Then the frequency, the resonance frequencies change, the eigenfrequencies changes, so this is now much higher. And then you can see that there is a certain area, quite a large area compared to what we have seen before, where there is very low amplitude for the motion of the car body. So that's the possibility how we can use the absorber over a broader range than was shown previously. Another thing is to see what is happening if we use a damped system. If compared to the previous diagrams, the damping rate is no more equal to 0, but we have a non-zero value for the dampers of the car suspension system and also a non-zero value for the damper that is connected between the car mass and the absorber. And in this case, we see much lower values for the amplitude of the car body and also lower values for the amplitude of the absorber mass. But we can also identify that the minimum value that we get for the car mass, the amplitude of the car mass, is no longer equal to 0, but it's a non-zero value. We can also have a look at what happens in the simulation, and we see there is a certain excitation. In fact, I think you can also see that the excitation is larger than the amplitude of the car mass, and all the energy that is put into the system through the excitation is in the kinetic energy of the absorber mass, but also dissipated in the two dampers that are connected to the system and where we have non-zero damping rate. Enjoy machine dynamics with MathWorks.